Yeah, in the morning class we have seen about counters, right? The up counters and down counters, right? Yeah. So, for example, uh, I'll see the one what we have seen in the morning, right? So this is an up down counter, right? So here you can see that your clock, right? Only for the first one you are using the clock signal, and all the other flip-flops are fed with different clock signals, right? Since we are using different clock signals for different flip-flops, we call these circuits as asynchronous circuit, right? Right? Asynchronous circuits, right? We have another type of counters, right, which are called synchronous counters, right? Synchronous counters. We'll see how we can design these synchronous counters, right? So HRONOUS, right? Synchronous, right? Synchronous counters. In synchronous counters, we are going to use flip-flops which are clocked by a same clock, right? For example, if we use a 3-bit counter, right, which means we need to use 3 flip-flops. Am I right? We need to use 3 flip-flops, and they will be clocked by a same clock pulse, right? For example, uh, if I draw this one, okay, we'll start from the JK flip-flop, right? I can search paper. Right. So okay, we can. I'll start from the basics again, right? I couldn't find it. It's a small sheet of paper. Right? Oh yeah, it's here. It's here. Right. So we have seen about J, K flip-flops. Actually, J is equivalent to set and K is equivalent to reset, I could say, right? So it is SR means J is actually set, right? J is set and K is reset, right? SR flip-flop, right? So when reset is 1, your output is 0. Am I right? When reset is 1, your output is 0. When set is 1, your output will be 1. Am I right? Your output will be 1. Clear? So this is the table, right? From this truth table, we can create the excitation table of this JK flip-flop, right? Excitation table is nothing but it's kind of a reverse engineering, right? What we can do is we can write J and K when we have Qn and Qn plus 1. Clear? For example, if Qn could be 0, 0, 0, 1, 1, 0, and 1, 1. There are no other combinations for both Qn and Qn and Qn plus 1, right? So Qn can change from 0 to 0, so it can remain from 0 to 0, or it can change from 0 to 1. It can change from 1 to 0, or it can remain, or it can keep in the same state as 1. Right. Now, from this table, we can extract this excitation table, right? Excitation table. For example, look at here. We have Qn plus 1 and Qn. Both are 0, right? For the first one. Right? We have Qn and Qn plus 1. Both are 0, right? So here we can see that, yeah, it is 0 here and it is 0 here. Am I right? At these two conditions, right? I have q n and q n plus 1. Both are 0. Am I right? So under that conditions, what is your j and what is your k? Right? See here, your j is 0, 0 and 0, 1. Clear? So I can say that whenever that 0, 0 will be kept constant, when your j must be 0 and k could be 0 or 1. Am I right? If you want to have qn as 0 and qn plus 1 as 0, you must have j as 0, right? Because it is 0 for both sides. At the same time, k could be either 0 or 1, right? For that, to mark either 0 or 1, I can use a don't care, right? So here I could make it as 0 and x. Am I right? So when I have 0, 0, that is, yeah, 0 and x. The next one is actually 0, 1. See here where I am having 0, 1. Yes, at this condition it is 0, 1, and then here it is 0, 1. Am I right? Under these two conditions, it is 0 and 1. Look at here. What are the combinations of j and k? Right, this one and this one. Right, so j must be 1, right? It is 1. K could be either 0 or 1. So I can say it as 1, don't care. Clear? 1 and don't care. Right, now go to the next one. 1, 0. Here it is 1, 0, and then here I am having 1, 0. Right, I have 1, 0. So equivalent is this one and this one. Right, see here I have j as 0 and 1, but k as 1 and 1, which means don't care and 1. Clear? Don't care and 1. Finally, we have 1, 1. Right, this is our 1 and this is our 1, 1. There are two chances. I can note them, which is 0, 0 and 1, 0. I could say that j is don't care because here 0 and here 1, but k is 0 and 0. Right, so I can write it as don't care and 0. Clear? So if you have a JK flip-flop with previous stage of 0 and next stage, means present stage of 0 and next stage of 0, you can predict that your J must be 0, but K could be either 0 or 1. Clear? At the same time, if present state is 0 and next state is 1, then you can predict that your J must be 1, but K could be a don't care. Clear? At the same time, similarly, when Qn is 0 and n1 0 might be don't care into 1 and don't care 0, right? Similarly. So this table is called as excitation table or state table, right? Present state, next state table. So we can call it as state table, or in some textbooks they have used the term excitation table, right? You can use any of them. Right, now let's see how we can use these state tables to our counters, right? To design our synchronous counters. For the synchronous counters, as I said, they have same clock pulse. Okay, I'll simply draw a 3-bit JK flip-flop, right? 3-bit synchronous counter, right? So I have clock, which is same for all, right? Which is same for all. I am using negative edge triggering flip-flop. Right, so this is my clock. This is my clock, and I have JA, KA. This is QA and QA bar. Right below, I will have QA bar. This is JB, KB. This is QB. B and QB bar, right? JC, KC, this is QC, and then I have QC bar at the bottom as well. Right, now if I want to design a 3-bit counter, for example, right, I'll consider it as a 3-bit counter, 3-bit up counter. Okay, so if it is a 3-bit up counter, the sequence these 3 flip-flop has to count is actually 0, 0, 0, 2, 0, 0, 1, 2, 0, 1, 0, 2, 0, 1, 1, 2, 1, 0, 0, 2, 1, 0, 1, 2, 1, 1, 0, 2, 1, 1, 1, 2, 0, 0, 0. Right? This is the sequence this counter has to count, right? So this is state 1, 2, 3, 4, 5, 6, 7, 8, right? And then we have the 9th state, right? To do a counter, right, or a synchronous counter, we need to write down the state tables, right? We need to do the state table. For example, if this is Qn, right, your Qn plus 1 must be this one, right? Qn plus 1. If 0, 0, 1 is your Qn, this must be your Qn plus 1. Likewise, this has to go it in a sequence, right? This should be going into a sequence. For that, I can draw a state table, right? So simply I can write it as a state table. This is my present state. This is my next state. Right? So I have 3 inputs. Am I right? I have 3 inputs which are 0, 0, 0 and right, 3 flip-flops, right? So I can name it the other way around, or I can put it in the reverse order, right? So maybe I can put it as C, B and A, right? C, B and A. Here C, B and A, right? So my present state, if my present state is 0, 0, 0, my next state must be, yeah, 0, 0, 1. If my present state is 0, 0, 1, my next state should be 0, 1, 0. Clear? Similarly, if my present state is 0, 1, 0, my next state must be 0, 1, 1. Clear? If my present state is 0, 1, 1, my next state should be 1, 0, 0. If my present state is 1, 0, 0, my next state should be 1, 0, 1. My present state is 1, 0, 1, next state should be 1, 1, 0. If my present state is, 1, 1, 0, next state should be 1, 1, 1, right? 1, 2, 3, 4, 5, 6, 7. And then if my present state is 1, 1, 1, my next state should be, yes, it should be 0, 0, 0, as we have seen here, right? So now we have filled a state table, right? So I can make it as, these are my Qn of JC, right? This is, QC, QB and QA. This is n plus 1 of QC, QB and QA. Or else I could say that this is Qn of C, right? The present state of this flip-flop, right? So now I can write the excitation table in the reverse order, right? I can write it as JC, KC, JB, KB, JA, KA, right? Using this table, right? Using this table. I'll show you, right? So see here, QC, right? For the flip-flop C, right? For the first state, which means for 0, 0, 0 to 0, 0, 1, I have 0 as my Qn and 0 as my Qn plus 1. Am I right? Right? For this state, I have 0 as my Qn and 0 as my Qn plus 1. For 0, 0, what I had for J and K? Yes, it is 0 and X. Clear? 0 and X. Similarly, you need to fill the whole table. Right? You need to fill the whole table, right? 0, 0 means 1x, right? So 0, 0 means 1x, 0, 0, 0, 0. So all these three are 0x, 0x, and 0x. Okay, thanks. Right? Similarly, if it is 0, 1, look at here. 0, 1 means 1x. Am I right? 0, 1 means 1x. 1, 1 means 0x. 1, 1, 0x, 1, 1, 0x, and 1, 0, x, 1. Clear? Similarly, you have to fill B. Now, to fill B, you need to compare the numbers in the middle row, right? So, 0, 0 is 0x, 0, 1 is 1x, 1, 1 is x, 0, 1, 0 is x, 1, 0, 0 is 0x, 0, 1 is 1x, right? This should be 1, right? 1, 1 is again x, 0, 1, 0 is x, 1. Clear? Similarly, you have to fill it for the A or the last one, right? So 0, 1, which is 1x, 1, 0, which is x1, 0, 1, 1x, 1, 0, x1, 0, 1, right? 1x, 1, 0, x1, 0, 1, 1x, and 1, 0, which is x1. Now you have truth tables for JA, JB, JC, KA, KB, and KC. Right now, you have to solve them in terms of Qn. Right? You have to solve them in terms of Qn. Right? Now we can solve them one by one. Right? Either you can use K-map or you can use simple Boolean equations. Right? We'll use K-maps. Right? We'll use K-maps. Right? First, we'll solve. Yeah, I could see that. See here. What I can say is KC equals, don't care, 1. Clear? Don't care, 1. I can say it as KC equals 1. Clear? At the same time, what is JA and KA? All are 1, right? This is 1 and this is 1. Even if you are drawing a K-map or not, it will be 1 and 1. Clear? So, JA equals KA equals 1. Clear? We can simply mark them as 1. Right. Now, what we need to do is we need to perform JC, JB, and KB. Right? Okay. For JC, what we have is actually this one and this one. Right? I would say JC equals QC bar, QB, QA plus QC, QB, QA, right? You can take QB, QA, QC bar plus QC becomes 1, and then I can write it as QB, QA. Clear? Right. At the same time, this one, right? JB, right? JB, I can say that, see here, these two are 0, right? And rest of them are 1. If I simply draw a simple K map, right? I can draw a K map. Okay. JB, I can draw a K map. QC, right? QC, QB, QA, right? QC, QB, QA. In the same order, what I have done is, oh, I can have, yeah, 0, 1, 2, 3, 4, 5. Oh, sorry, not that one. 0, 1, 2, 3, 5, 6, 7, right? Which means 0 and 4 are 0, right? 0, 1, 2, 3, 4 are 0, and then 1 is 1, 5 is 1, 0, 1, 2, 3, 4, 5, 6, 7, and all the others are don't cares, right? All the others are don't cares. All I can simply do is I can make it as a quad, right? Box of 4, right? Then I can name this as, right, sorry, 0, 0, 0, 1, 1, 1, 1, 0, 0, and 1, right? So see here, A is common, right? So I can write it as JB equals QA, right? JB equals QA from the K map. Now we need KB, right? We need KB, right? Now, okay, check the third column. Any problem with this one? 0, 0. Where we have done the mistake? Can you unmute and talk to me? Is it this one? Oh, which one you are talking about? Hello?
Sir, the first one, the JK, the first column.
This one?
Yeah.
Where we had the mistake?
Can you tell again that column?
How these come?
Yeah, no, please check. I think wrong.
Which one is wrong?
Wrong.
1, 2, 3, 4, 5, 6, 7, 8. Which one is?
One.
This one. Right. So we have 0.
Sir, one. Yeah.
Yeah, 1, 1 is 0x. Sorry, x0.
X0. Yeah.
Right. Okay.
All.
Right. Yes. Thank you. So this must be x0, right? Thank you.
Okay.
All these must be x0, but still it will be okay. Why? Because yeah, they are interchanging. But thank you for noting it, right? Please be careful, right? And message me if you have any doubts. Please, if you have anything, if you found anything wrong, please let me know, right? Okay, right. That's correct. Right, but it is not going to change our values, right? Because they are don't cares, no. JC and KC, right? JC was, yeah, still they are don't cares, no, right? Sorry, JC was, yeah, this one, and yeah, I could say, oh, I can remove all the others, right? They could be don't care if we do, and KC as well, right? KC, I can write it as, okay, I'll write the K map for KB first, right? I'll write the K map for KB first. Right, KB, this is QC, QB, QA, right? So 0, 0, 0, 1, 1, 1, 1, 0, 0, and 1, right? KB means this one, right? So this is 0, don't care, 1, don't care, 2, 0, and 3, 1. 4 don't care, 5 don't care, right? 6 is 0 and 7 is 1. Am I right? Again, I can have a same thing, right? So I can write it as KB equals, I would say, QA, right? JB equals QA and KB is also QA, right? So now JA equals 1, KA equals 1, JB equals QA, KB equals QA. Of course, we'll do a K map for JC, KC as well, right? Since we have changed the values. Okay, keep this one. Right, we'll do that one in the K map as well. Right, so now right, so now okay, let's see how that JC, right? JC again. QC, QB, QA, right? 0, 1, 0, 0, 0, 1, 1, 1, 1, 0, right? See here, it is 0, 0, 0, 1, clear. And then, yeah, 4 is don't care, right? Don't care. And then, yeah, for 1, 0, it is, sorry, let's let it. Oops. Yeah, see it. For 1, 0, it is x1, right? Don't care, 1. So this one also, we can have it as don't care, right? Or simply, I can group this one, right? I can have a group this one where my JC equals, both are 1, right? I could say it as QA, QB. Clear? JC equals QA, QB. Similarly, we'll do the K map for KB as well. We'll do the K map for QC, QB, QA, right? We are using in the same order 0, 1, 0, 0, 0, 1, 1, 1, 1, 0. Right? See here. So don't care, don't care, don't care, don't care. 0, 0, 0, 1. Am I right? And then similarly, I'm going to have the same thing. Right? So my KC equals again QA, QB. Clear? So I can write that, right? So that KE leave that KC, right? So it is not 1, right? So we have changed it, right? So I can write that my JA equals KA equals 1. Am I right? From this one, because yeah, all these, right? So 1 don't care, 1 don't care. I can take it as 1. Clear, right? From this table, I took it as 1. And my JB equals KB equals QA. Am I right? JB equals KB equals QA. Right. Similarly, JC equals KC equals QA, QB. Clear, right? So I have JC as QA dot QB, while I have JA and KA as 1. Right now, I need to draw the circuit. I need to draw the counter circuit using these 3 inputs, right? So now I'll draw it in the same order, right? First, I can put my A, right? I can put my A, B, C, right? This is A, B, and C. All of them are powered by the same clock. This is my clock, and JA equals KA equals 1. Am I right? This is high, or 5 volt, or 1, or 5 volt, whatever, right? So this is my JA, KA, right? And then this is my QA, right? Look at here, what are my JB and KB? This is my JB and this is my KB, right? Both are QA. Clear? Both are QA. Similarly, what is my JC and KC? Yeah, they are QA dot QB, right? Let me have QB here, right? So this is my QA, and then I can put it into an AND gate, and that is my JC and KC, right? This is my QC, right? So I can get the output from QA, QB, and QC. Clear? So the output from these will be my counter, and if you run this circuit, right? If you run this circuit will count a sequence of 0, 0, 0 to 1, 1, 1, right? Using this circuit, you can design any kind of counters, right? You can design an up counter or a down counter or an irregular counter, right? Okay, I'll do another example, right? I'll do another example. Right, so for example, you are asked to design a circuit to count a sequence of a 3-bit sequence of 1, 3, 5, 7, right? It is odd number sequences, right? 1, 3, 5, 7, and then again 1, 3, 5, 7. Right? I would say it as a state. I would write it as a states, right? So 1 is my first state, 3 is my second state, 5 is my third state, and 7 is my fourth state. And then from 7 I have to get 1, right? So I could say that this is 1, 2, 3, 4. So I need to design an asynchronous circuit which can count from 1, 3, 5, and 7. So if my present state is 1, my next state will be 3. Am I right? If my present state is 3, next state is 5. If my present state is 5, next state is 7. If my present state is 7, my next state is 1. Right? If I write it in binary, or I can write the state table as, right? So this is my PS, this is my NS, right? So 0, 0, 1, right? Which is 1. My next state will be 3, right? Which is 0, 1, 1, right? And then if my present state is 0, 1, 1, next state is 1, 0, 1, right? Which is 5, right? This is 0, 0, 1, 0, 1, 1, 1, 0, 1, then 1, 1, 1, right? If my present state is 1, 0, 1, my next state is 1, 1, 1. And if my present state is 1, 1, 1, my next state should be 0, 0, 1. Clear? So which has 1, 2, 3, 4 steps, which is 1, 2, 3, 4 transitions. Now what we need to do is we need to draw the the JAKB, right? So we can write it as if it is CB or any order, right? So let's take it as QC, QB, QA, right? QC, QB, QA, right? So this is my QC, QN plus 1C, QN plus 1B, and A. Right, now we'll fix the K map, right? Sorry, the excitation table, right? JC, KC, JB, KB, JA, KA. Right, now we need these two tables, right, to fill it, right? We need the excitation table and this one to fill it, right? So 0 0 0 x, 0 1 1 x, 1 1 x 0, 1 0 x 1. Clear, right? That's for C. Now compare B. 0 1, right? 0 1 is 1 x, 1 0, which is x 1, 0 1, which is 1 x, and 1 0 x 1. Clear? Right, now look at here, all 1 and all 1, am I right? QA all 1 and 1, right? 1 1 is actually x 0. Clear? X 0. Now you can solve them using a K-map, right? You can solve them using a K-map. I would simply write this as 1, this as 1, this as, of course, 0, this as 0, right? Because they are don't cares. Clear? They are don't cares. I would say I would take it as 0, right? For this one and this one only, I need to draw the K-map. Clear? Oh, I could write. Oh yeah, I have a don't cares as well, right? I have a don't cares as well. So let me draw K-map for this one and this one only, right? For JC, right? This is QC, QB, QA. 0 0 0 1 1 1 1 0 0 and 1, right? What I can do is, of course, what is JC, right? 0 0 1 is 0, right? So that is 0, right? 0 1 1 is 1, and I could say, or I could mark all the others as don't cares. Am I right? I could mark all the others as don't cares, and then right? So it becomes simply QB, QA, right? QB, QA. And similarly, for KC, you have 1 1 1 is 1, which is this one, right? 1 1 1 is 1, and this one is 0 again. All the others as don't care. Clear, right? So for if you fill it for JC, I could take it as C here. 1 0 1 is 0, which is 1 0 1. This is 0, and 1 1 1 is 1, and all the others as don't care. Similarly, I have the same group, right? I have the same group. So I could say that JC equals KC equals QB, QA, right? And JB equals KB equals 1, right? JA equals KA equals 0. Right, now you can draw the circuit simply, right? Okay, I'll draw it. Right, we can draw the circuit, right, which is simple, right? So I have 3 flip-flops. Right, so my JA, KA equal to 0, right? This must be A, B, and C, right? JA, KA must be grounded, right? JA, KA, right? And then I have my clock. For all of them, I have the same clock bells. Right? And then my JB, KB equal to 1. Right? So they can be connected to a high high, 5 voltage or whatever you like, right? Then this is my QA, this is my QB, and my JC is actually QA, QB, right? What I can do is, this is my QA, right? Of course, I can take it from here. This is my QB, put it into an AND gate. Yeah, this is my JC, and the same is my KC. This is my QC, right? So this is the sequence or kind of an irregular counter, right? This is how designing an irregular counter. Now, I think that's all about your counter or the sequential logic circuits, right? That's all about your sequential circuits in your in the advanced electronic course, right? So now you can do the question number 5 in all your past papers. Clear? You can do question number 5 in all your past papers. If you have, right, so I would advise you to practice all of them, and if you have any questions or if you cannot do anything, right, if you have some problems with any questions, please let me know, right? So if we miss, and I just want to know whether we have missed something or not. Okay, so any doubts or any questions you can ask me now. Right, similarly, right, similar to this one, you can make an excitation table for SR flip-flop as well, right? SR or T or D flip-flop, right? And we can see how we can use the other flip-flops as well, right? So just go through your past papers, all the past paper questions, and if you found anything wrong, any difficulties, please let me know, right? Any questions in this section?
Till now, no, sir.
Huh?
Like, till now, no, sir. When we have any questions, we'll ask. Any
Yeah,
doubts?
so now
And
can do question number 1, right? Question number 1, which is BJT and FET, right? And then question number 4, which is combinational logic. Right, and question number 5, which is sequential logic. Right, and you are able to do half of the question number 3, which is op-amp. Right, so we have 1.5 question left, right? 1.5 unit left. Clear? Right, I'll try to finish the sections by the end of next week. Right, we can complete the syllabus by the end of next week, and then what I advise you to do is try to solve all the problems in your past papers, right? And I will upload maybe a couple of past tutorial questions, right, for your practice. Okay, if you have any questions, please let me know, but I would strongly advise you to try the past paper questions. Okay, any questions?
We'll do the past papers and then.
Yeah,
okay, Janit.
sir, out of the questions today evening section, I didn't see the notice that there will be another lecture in the evening time. That I mean this lecture. So I came half of the lecture gone after the lecture.
Okay.
So could you please upload the evening lecture recordings to the YouTube